Hi everybody, welcome to section 12.6 on cylinders and quadric surfaces. So we're going to start off by reviewing these two-dimensional conic sections. Now while a conic section is two-dimensional, if we look at all these different types of equations for conic sections of a circle, ellipse, parabola, and hyperbola, you can see that all of these equations only contain the variables x and y. So these are all two-dimensional. However, they can be formed by taking a cone and cutting a cross section of a plane into that cone. So we can see in all four of these cases, all of these shapes, all of these conic sections can be made by intersecting a plane and a cone. That intersection is then each one of these conic sections. So a circle is something we should be fairly familiar with. We know the equation of a circle is x squared plus y squared is equal to, and now we usually just call this r squared because we know this a is just going to be the radius of the circle. Now an ellipse is like a circle, except its height and its width are not the same. So if we have two ellipses, we're going to have one that has the major axis on the x-axis and the other with the major axis on the y-axis. So the major axis is just the furthest distance between any 2 points on an ellipse. So in this case, our major axis is the x, and in this case, our major axis is the y. So let's think, how can I tell what the major axis is by looking at the equation of an ellipse? Well, for example, we have the equation x squared over 4 plus y squared over 9 is equal to 1. So we know that this is the equation of an ellipse. And we know that ellipse is going to have a major axis that's either the x or the y. So if I want to find the graph for this ellipse, what I can do is I can say, okay, let's find these intercepts with the axes. So if x is 0, I'm looking for that y-intercept. I know that I have y squared over 9 is equal to 1, and so y must be 3 and negative 3. So 3 and negative 3. If I plug in a 0 for that y value, I get x squared over 4 is equal to 1, leaving me with an x of positive or negative 2. In this case, because this ellipse is taller than it is wide, we can say that the major axis is the y-axis. And in this case, if I use these variables a and b, well, to denote the constants in the denominator here, I saw that in this case a was less than b, and since a was less than b, my major axis was the y. So our ellipse is going to look something like this if our a is less than b, and something like this if our a is greater than b. Okay, so this is how we're going to categorize an ellipse, just with stating the major axis, which one it is. Now for a parabola, we've got 4 different shapes of a parabola in general. We've got a parabola that looks something like this. We know that's going to have the equation y is equal to x squared. We know if our x squared term is negative, our parabola looks something like this. That's going to be y equals negative x squared. Our parabola can open to the right, and that's going to be x is equal to y squared. And our parabola can open to the left, and that equation is going to look like x is equal to negative y squared. So we've got these 4 different parabolas. Now the good thing is that in Calculus 2, we went over how to graph different types of equations and how to use the parametric mode to graph something in the form of x equals something in terms of y. So if you're looking at an equation and you forget what it might look like in 2 dimensions, you can absolutely graph that. So we have our parabola. Now this 4 just comes from the definition of a parabola, where A is the foci of the parabola, of each parabola, and there is a proof for that. I'm more than happy to give that to you if you are interested. But in general, we just know that our parabola is going to just be either x squared or y squared is equal to something. That's all we really need to know for now. So now for our hyperbola. We're going to categorize our hyperbola in 2 different ways. One in which this hyperbola opens to the left and to the right. So a hyperbola kind of looks like 2 parabolas on each side of these axes. And we can categorize a hyperbola like this by listing our conjugate axis. So our other option for a hyperbola is one that opens upward and downward. And let me draw this a little bit better just to show that symmetry. All right. And I can describe a hyperbola using the conjugate axis. The conjugate axis is just the axis which this hyperbola does not travel through. So it's in between our 2 parabolas. And this conjugate axis in the first hyperbola is y. And in this second hyperbola, our conjugate axis is x. And when we have an x squared over a squared minus y squared over b squared is equal to a positive 1, it's going to have the conjugate axis being y. When we have x squared over b squared minus y squared over a squared is equal to negative 1, we're going to have that conjugate axis of x. So these are 2 different types of hyperbolas. So now let's look at these examples here, and we're just to identify each of these conic sections. And over to the right here, we just have a little summary that we can look at that might be helpful. Now you'll notice that in these general equations, let's look at the first example. So we've got this x term, we've got a y term, and we've got a constant. But over here in our general equations, we are just worried about those leading terms, so the terms with the highest degree, both x and y. So that's what we're going to focus on. So in this first equation, 9x squared minus 25y squared minus 18x minus 100y minus 316 is equal to 0. All we're worried about is this 9x squared minus 25y. And maybe if something's negative or positive depending on the equation, but I'm going to start by focusing on this 9x squared minus 25y. And I'm saying, okay, do I have only an x squared or y squared? No, I have both an x squared and a y squared. Do I have the same number in front of x squared and y squared? No, I do not. Do I have a different number in front of x squared and y squared with a plus sign? Nope, I see a negative. And do I have a different number in front of x squared and y squared with a plus or minus sign? Yes. And this wording might be a little confusing with a plus sign or a minus sign. This really means one of each of those signs. All right, so yes, so we know that this is a hyperbola. And now that we know that this is a hyperbola, we want to find out, is the conjugate axis y, or is it the conjugate axis x? And because by moving this 316 over to the right-hand side, we can see that this would give us a positive on the right-hand side of the equals sign. We have something x squared minus something y squared. We're going to have this first version of that hyperbola with a conjugate axis of y. And that is all we need to really know about this conic section by looking at that equation. B, we've got y squared plus 6y minus 4x is equal to 1, and we said we're only going to worry about the terms with the highest degree. In this case, that's 2. So now we're only looking at the y squared term. And over in our categories on the right here, if we have only x squared or y squared, that means we have a parabola. And in this case, we definitely do have a parabola. And now how does this parabola open up? Well, if I were to take that x and move it over to the right, don't we agree that this is going to look something like x is equal to y squared? Right? So this parabola is going to open to the right. It's going to look something like this. C. 4x squared minus y squared minus 16 is equal to 0. So I'm looking at this 4x squared minus y squared. I see we've got different signs, so we've got one positive and one negative sign. And that's going to tell me that this is a hyperbola. Now, is it a hyperbola with a conjugate axis of y or a conjugate axis of x? If I move this 16 to the other side, I'm adding 16, and then I have something that looks like x squared minus y squared equals a positive number. And so it's going to look like this first equation. And so it's going to be a hyperbola with a conjugate axis of y. D. 9x squared plus 25y minus 54x minus 100y minus 44 is equal to 0. We are worried about this 9x squared plus 25y. Well, I see different coefficients in front of the x and y squared terms. I see a plus sign, and so that tells us that this is an ellipse. And so we've got an ellipse. And when we have an ellipse, our question is, what is the major axis? Is it x and y? And in our formula for an ellipse, these coefficients are in the denominator. So we've got x squared over a squared. Now, if a squared is greater, that means that my x squared term is really smaller. If I have a larger denominator, that means this term is smaller. So another way I could say that is that if I have the major axis of x, that means that I have a larger coefficient attached to the y squared term. So what's the which coefficient is bigger? Well, the coefficient attached to the y squared term is bigger, meaning our conjugate axis is going to be x. It's going to look something like this. Our major, I'm sorry if I said conjugate, now we're talking about a major axis of x. E, we've got x squared minus y squared plus 6x minus 8y equals 107. So I'm looking at this x squared minus y squared. Because I have a minus in between these two terms, this looks a whole lot like a hyperbola. And if I get this constant and I bring it over to the other side, it's going to be positive. And so again, we have a lot of these examples where this is a hyperbola with a conjugate axis of y. F, 9x squared plus y squared plus 9x minus 4y equals 0. I'm looking at this 9x squared plus y squared. I've got different coefficients in front of the x and y, and I've got a plus sign between them, which brings me to this ellipse. So we've got an ellipse. And now we want to know if the major axis is x and y, and we said that whichever of these coefficients is larger, the other variable has that major axis. Because the coefficient attached to the x squared term is larger, I know that our major axis is y. Okay, 3 more. X squared plus y squared plus x is equal to 0. We've got a plus between them. We have the same coefficient for x and for y, and that brings us to a circle. And in a circle, there is no major axis, there is no kind of conjugate axis or anything like that, so we can just say this is a circle. That is plenty of information. 9x squared plus 25y squared minus 225 is 0. Well, I've got a plus sign between them. I've got different coefficients attached to x squared and y squared, and so that tells us that this is an ellipse. And so we have an ellipse, and we want to find the major axis. Well, because the coefficient of y squared is larger, that means that our major axis is x. And finally, y squared minus 2y minus 6x minus 2 is equal to 0. I just see a y squared term, and so I know that this is a parabola. And how does this open up? Well, if I take this 6x and I pull it to the other side, this looks a whole lot like y squared is equal to positive x. And so I can say that this opens to the right. All right, so now we know how to describe all of these different types of conic sections in 2 dimensions. So we're going to move along to 3 dimensions. Now, the important part of this is that we refresh ourselves on some of that vocabulary, learn about the different types of conic sections so we can apply this to 3 dimensions. And we have this little sort of cheat sheet here on converting to HK form. So if we're given something in standard form, for example, if we're given this expression, it's in standard form, let's see. We know because we have a plus sign between the x and y squared terms, it's an ellipse because it has different coefficients. So this is some kind of ellipse. But looking at the standard form of the equation, that's really all we know. We don't know where the center of HK is. We don't know what that major and minor axis is. Well, we just know that the major axis is x, but we don't know the length of those major and minor axes. And so to get more information, we want to convert this to HK form. And we do that by completing the square. And we'll complete the square for each of these variables. And we're not going to go through something like this because we did already talk about this kind of stuff in previous math classes earlier in calculus, but this is just something for you to look at if you forget that process, especially as you're going through things like homework. So we just have this as kind of a resource for you to refresh your memory. And now we're on to new content. So we're starting off with cylinders. So for our cylinders in 3 dimensions, in order to sketch a 3-dimensional graph in general, it's really useful to determine the curves of intersection of the surface with these planes parallel to our coordinate planes. So planes parallel to the xy plane, the xz plane, and the yz plane. And these curves are called traces, or we could just call them cross sections of the surface. All right. And so this is our method for drawing these 3-dimensional figures because we want to draw the traces in R cubed. And what this really means is that we are going to use the traces of each of these graphs to just sketch these figures in 3-dimensional space. Now we're told that we are on the section of cylinders. Now how do we know something is a cylinder? Well, let's look at these 3 different equations, and what do we notice? Well, we've got an x and a y squared term, but we're also missing a variable. This first equation is missing z, this first equation is missing y, this third equation is missing x. So we know it's a cylinder when this is missing a variable. And whatever that missing variable is, we're just going to let that be equal to k. Let's see what this means. I have x squared plus y squared equals 1. Well, I know that in our so in our two-dimensional coordinate system, what's this going to look like? I know this is going to be a circle with a radius of 1 in my two-dimensional coordinate plane. So now in 3 dimensions, how does this change? Well, I know that what this tells me is that if this were in 2 dimensions, so if z is equal to 0, this is what that graph would look like. So when z is equal to 0, we have a circle with a radius of 1. And I can draw that as a circle with a radius of 1 when z is 0. Well, what if z isn't exactly equal to 0? What if z is equal to 3? Well, if x squared plus y squared is equal to 1 and z is equal to 3, that would look like a circle at z is equal to 3. If z is some negative value like -3, then again we would have a circle at z is equal to -3. And what happens when we can have any value of z, but our x and y values must fulfill this equation x squared plus y squared is equal to 1? Well, then we have a cylinder. The cylinder is going to go up and down infinitely. And let's describe the cylinder a little bit. Well, we know that this cylinder is centered around the z-axis. And so let's look at this equation to see if we can maybe figure out some kind of conclusion. We found that the cylinder is centered around the z-axis. And we can see in this equation that z is the only variable we're missing. So now let's conclude that in the equation of a cylinder, we're missing a variable. That variable is the axis. Now let's look at B. Well, now that we've concluded that we have a cylinder, so if we were just looking at the x and z variables, this looks like a circle. We know that the missing variable is the variable of the axis. And so because this variable isn't included in the equation, we're missing y, we can say that y is equal to anything. That anything, let's just call k. So we can include the equation y equals k because we know we need to include these constraints for 3 dimensions. And in our 3-dimensional coordinate system, we've got z, y, and x. We know that our trace in the direction of the xz plane is going to be a circle with a radius of 1. We know this is going to go along the y-axis. Just extend that in the negative direction. And so this will look like a cylinder. Centered around the y-axis. All right, one more. For C, the variable we're missing is x. So we can say that we have some x is equal to k, a constant. And if we draw that three-dimensional system. Since our variable of x is missing, we know that this is going to be centered around the x-axis. Because we have the circle y squared plus z squared is equal to 1, that means that the trace on the yz plane is going to look like a circle. So we're going to have a circle centered around the x-axis, going infinitely in the x direction. And while we're drawing a cylinder with a definite end here, we really know that this cylinder in part B is going to continue infinitely in the y direction, and this cylinder in part C is going to continue infinitely in the x direction, unless we have some other kind of constraints. So we can say that in part C, this is a cylinder that is centered around the x-axis. Now let's talk about the actual traces of these cylinders. So if we were to cut this vertical cross section in this first cylinder, now we already talked about the cross section. If we were to cut this on the y-x plane, the xy plane, it would look like a circle. What about on the xz plane? And if I imagine that I am placing a plane through this cylinder and I want to know what it's going to look like on the xz plane, well, if I look at this cylinder from the sides, all I'm going to see is these two parallel lines. So the trace on the xz plane is going to look like two parallel lines. All right, finally, what about on the yz plane? If I'm looking at the yz plane, and this one's a little bit easier to see because we're sort of looking at this in the direction of the x-axis, so we're sort of looking at that yz plane, and again, we can see that we would just see two parallel lines. And so these are our three traces. We have our trace on the xy plane, we have our trace on the xz plane, and we have our trace on the yz plane. So this is what we're talking about with those traces. Now a cylinder, it's a little bit easier to picture a cylinder in 3 dimensions, but for some of our more complicated figures, this method of looking at these 3 traces is going to come in handy. Example 3, we want to sketch the graph of the surface z is equal to x squared. Well, z is equal to x squared, doesn't that look a whole lot like a parabola? We know that the parabola y is equal to x squared looks something like this. So what about z is equal to x squared? Well, if this is the y-axis and this is the x-axis, then we know that if we have the z-axis and the x-axis, then we will have an upward-facing parabola. So this would be the equation z is equal to x squared. But then what about y? And because we have the variables z and x, we know that this is in 3 dimensions, and so we can say that y is equal to k. In other words, when we just say y is equal to k, it means y can be equal to anything. So now let's draw this in 3 dimensions. Now, we know that on our xz plane, we have this parabola. So I'm going to try to draw something that depicts a parabola on the xz plane. And then if y is equal to anything, when we're missing a variable, we know that this is going to be the axis. Y can be anything. Well, then I know that this extends infinitely in the positive y direction, and I know it extends infinitely in the negative y direction. This is a little bit difficult to draw. But we are going to have something that looks like this. That extends infinitely in the positive and negative y directions. And this is called a parabolic cylinder. Now typically, we've seen cylinders that look like this, and more specifically, these are called circular cylinders. Another way we can describe a cylinder in general is that it consists of all lines called rulings that are parallel to a given line and pass through a given curve. So in this case, that given plane curve is z is equal to x squared, and we can really construct this with a series of these parallel lines. Right, so we can draw an infinite number of parallel lines that lie along this curve z is equal to x squared. That's just an alternate definition for our cylinder. So this is called a parabolic cylinder. Now we notice that the y variable is missing from this equation, and so that's going to be the axis on which this cylinder lies. Now it's important to note that when we're working in 3 dimensions, something like x squared plus y squared is equal to 1, this represents a circular cylinder and not a circle. This has a trace that's a circle in the xy plane, but it is not a circle. And to include that 3rd dimension, we can say that we have x squared plus y squared equals 1, and z is equal to some k. So now for our quadric surfaces. A quadric surface is the graph of any equation that can be put into this general form, mainly with an x squared, a y squared, and a z squared component. So it's going to be a 3-dimensional surface in some space. A, B, C through J, so all of these capital letters are constants in this equation, and then also any quadric surface by translation, which just means moving it in a certain direction, and rotation, it can be brought into one of these 2 standard forms. So let's look at our first example. So there are 6 different types of quadric surfaces, and let's look at each example. So we've got our ellipsoid. An ellipsoid is a 3-dimensional surface because while it looks like it might be some figure, it is not solid in the middle. So it's some surface in the 3-dimensional coordinate system for which all traces are ellipses. That means that our trace in the xy plane in the xz plane and in the yz plane are all ellipses. And we have this website as a resource for you, so let's go look at this. On this website, we have this really good simulator for these different types of quadric surfaces in which we can visually see the traces. Now it might be a little bit hard to see, but this website is attached to your notes, so you should just be able to go there and get a better picture. But this is what our ellipse is going to look like. So if we go down here, we have our x, y, and z traces. So we can look at the traces where x is equal to some certain value, so on the yz plane. And when we bring this plane into this ellipsoid, we can see this orange line here, how no matter where this plane is inside of the ellipse passing through it, this trace is going to be an ellipse. So in our ellipsoid, and we're going to see that for any y value that's valid, so any trace on the x-plane, and we're going to see that for any trace on the xy plane where z is equal to some value. So all three of these traces in an ellipsoid are ellipses. All right. And if A, B, and C are the same, that means this ellipsoid is a sphere. Just like in 2 dimensions, when our coefficients of x squared and y squared are the same, then we know that this is a circle. If not, then it's an ellipse. So let's actually look at these traces. On the xy plane, what that means is that we're going to represent this missing variable z with some constant k. If z is equal to k, then we can write this trace as ax squared plus by squared plus ck squared. And now, if k is just some constant, we're multiplying this c by another constant. I can just say that that's equal to k squared is equal to 1. Now to better see what this shape is, let's bring that constant to the other side, and we're left with ax squared plus by squared is equal to 1 minus k squared. And in this case, when we just have a constant on the right-hand side, we can see what shape this is. If a is equal to b, then this trace is going to be an ellipse. And if a is not equal to b, this trace is going to be an ellipse. And if a is equal to b, then this will be a circle. On the xz plane, our y value is going to be some k. And let's just pull that over to the other side. We know we're going to plug, and let's look at this form of it. We know we're going to plug this k in for y, and so we're going to take this 1 minus that k squared. And so we're going to have something in the form of ax squared plus cz squared is equal to 1 minus k squared. And in this case, if a is not equal to c, then this trace will be an ellipse. And if a is equal to c, then this trace will be a circle. We're going to see the same pattern here. In the yz plane, our x value is going to be some k, and the equation of that trace will be in the form of by squared plus cz squared is equal to 1 minus k squared. And in that same way, if b is not equal to c, then this trace is an ellipse. And if b is equal to c, then this trace is going to be a circle. All right, so this is for our ellipsoid. Next we have our elliptic paraboloid. So an elliptic paraboloid is in the form z equals ax squared plus by squared. It can also be written in the form y is equal to ax squared plus cz squared, or x is equal to by squared plus cz squared. So it just depends how this elliptic paraboloid is oriented, if it's facing upward, facing to the x-axis, or facing toward that y-axis. And you can see that the y and x here are flipped, but that does not affect the shape of this, and we will see why. So now let's look at our traces. let's look at the xy plane. The xz plane, and the yz plane. Well, in the xz plane, we can say that our z value is some k. And let's just look at this most standard form of the equation with this elliptic paraboloid facing upward. So that will give us something in the form k is equal to ax squared plus by squared. And what does this look like? Well, this is just ax squared plus by squared is equal to a constant, which is either an ellipse if a and b are not the same, or a circle if a is equal to b. So this will give us that ellipse or circle. So that is this horizontal trace. Now for our vertical traces, we have the xz plane. In the xz plane, we know that our y value is equal to k. When we plug that in our equation, we get z is equal to ax squared plus some constant times k squared. And what does this look like when we have z is equal to ax squared plus k squared, remembering that this is just a constant? Well, that looks a whole lot like a parabola. And we can see that on the xz plane, this trace is that parabola right along here. Finally, in the yz plane, that means that we're going to call x some k. Plugging that into our equation, we get z is equal to a times x squared. Let's call that k squared plus by squared. Again, remembering that this k squared is just a constant, we know that this is in the form of a parabola. And generally, when we substitute this variable for k, we just kind of discard the accompanying coefficient on the end of that, which is just why we call this k squared. That's just kind of standard here, but either way, we know that this is a constant. And so this is what our elliptic paraboloid is. Our horizontal traces are ellipses, and then our vertical traces are parabolas. And we have that the variable raised to the first power indicates the axis of the paraboloid. And so this is the first equation here, and z is raised to the first power, which means the axis of this is the z-axis. And you can play around with those traces at this URL here. So our hyperbolic paraboloid, this is sometimes called a saddle for obvious reasons. Now, just like with that other equation, this can also be written in the form of y equals ax squared minus cz squared, and x is equal to by squared minus cz squared. And this is the last one that we're going to look at the traces, because I think this is one of the more confusing shapes. So we are looking at the xy plane, in which z is equal to some k, and the trace that lies along the yz plane, in which x is equal to some k, and finally the trace that lies along the xz plane, in which our y value is equal to some k. Alright, so in our xy plane, our z is equal to some k. When we plug that in this equation, we are just left with k is equal to ax squared minus by squared. And what is this in the form of? Well, if we look back at our first page, this is in the form of a hyperbola. And more specifically, when this value of k is positive, our conjugate axis is going to be the y-axis. When this is negative, then our conjugate axis is going to be the x-axis. So this is where it gets a little bit complicated. So let's go to this website and look at this in 3 dimensions. So if we're moving this plane and our z is negative, we can see that we have this hyperbola oriented in a certain direction where the x-axis is the conjugate axis. Now watch what happens. Watch closely what happens when the z turns from negative to positive. Now we can see that the orientation of this hyperbola is flipped. And now our y-axis is the conjugate axis. And that's what makes this, I think, a little bit difficult to picture and even more difficult to draw. Because this hyperbola switches its orientation at z is equal to 0. So let's look at those other traces. On the yz plane, we know that x is equal to some k, and so we have an equation in the form z is equal to k squared minus by squared. Because k is a constant and y is the only variable that's squared, we know this is going to be a parabola. Finally, when y is equal to k on the xz plane, we have an equation of the form z is equal to ax squared minus k squared. And again, because k is a constant, this is also going to be a parabola. So, this hyperbola is going to open toward the x or the y-axis depending on the value of z. Now this parabola over here, we have z equals negative by. That is going to be opening down around the z-axis. Alright, this parabola over here, going through the xz plane, because this term is positive, this x squared term is positive, it is going to be opening upward. And we can sort of see that in our little diagram here. We can see this hyperbola here and here, this horizontal hyperbola. We can see the parabola facing downward, and we can also see this parabola facing upward. All right, so this is our hyperbolic paraboloid. Now the next shape isn't quite as complicated, and for that reason, we're just going to talk about the last few of these without looking at these traces very closely, because hyperbolic paraboloid is really as complicated as it gets. And then we'll look at the traces by doing some examples. So a cone is in the form of z squared is equal to ax squared plus by squared. Notice that we can exchange this variable, so we can call this y squared is equal to ax squared plus cz squared, and x squared is equal to by squared plus cz squared. All right, the horizontal traces are ellipses. And we can see that if we look at a horizontal trace around this cone, we can see that that will give us an ellipse. Now it'll give us a circle if our A and our B values are the same. Our vertical traces are hyperbolas if k does not equal 0, but are pairs of lines if k is equal to 0. All right. If I can imagine slicing through this cone and creating some sort of vertical slice through this cone, I can see that cross section, if I sliced this cone in half, is going to look something like this. And that's why we can say that if k is equal to 0, then this looks like two pairs of lines if we slice through the middle or right along this z-axis. Now if we don't quite slice through the middle, but instead we slice through this plane that's not quite in the middle of this thing, then we can see that these traces are going to form this hyperbola. It's a little bit difficult to see, but we can see that if we cut through with this green plane, then that trace is going to be a hyperbola. And a really good example of this that's much better drawn is the part that talks about the conic sections on the first page of this note sheet. It shows that perfectly. All right. Next, we got our hyperboloid of one sheet. So a hyperboloid of one sheet just has these horizontal traces that are ellipses, and we can see these shaded in gray, and then the vertical traces that are hyperbolas. The axis of symmetry corresponding to the variable whose coefficient is negative. So in this case, because our z squared value is negative, that means that this is going to be oriented along the z-axis. And the important thing here is either x squared or y squared or z squared is negative, meaning we have one negative. Finally, the hyperboloid of two sheets is very similar with one exception. That is that our hyperboloid of two sheets has two negatives. All right, horizontal traces are ellipses if k is greater than c or if k is less than negative c. That just means that where these horizontal traces exist. We can see if we try to take a horizontal trace here on the xy plane, so where z is equal to 0, we wouldn't get any real space. We wouldn't get any kind of plane here. So just within this region, our horizontal traces are ellipses, and our vertical traces are hyperbolas. Okay, a good way to remember it is that the two minus signs indicates two sheets. So hyperboloid of one sheet has one negative sign, hyperboloid of two sheets has two negative signs. So now let's do some examples. I know we talked about a lot of abstract ideas. Let's look at some examples. Example 4. We are going to use traces to sketch the quadric surface with the following equation. So using our traces, we are looking at the xy plane. The xy plane, our z is going to be equal to 0. When z is equal to 0, let's plug a z is going to be some k. It can be 0, but it's going to be some k, so let's plug that into this equation. We get x squared plus y squared over 9 plus, and now I'll call this k squared over 4, just a k squared, being equal to 1. So let's move this constant to the other side of the equation. So we've got x squared plus y squared over 9 is equal to 1 minus k squared. And if we forget what kind of shape this is where that review of conic sections really comes in. Now we've got positive x squared and y squared terms, but we do not have the same coefficient. And so this is going to look like an ellipse. And so we've got an ellipse on the xy plane. All right, let's look at the xz plane, where y is going to be equal to 0. Well, when y is equal to 0, this equation is going to look like x squared. I keep doing that. Y is equal to k. X squared plus k squared plus z squared over 4 is equal to 1, meaning I can rewrite this as x squared plus z squared over 4 is equal to 1 minus k squared. All right, because my x squared and z squared terms are both positive, and because our coefficients are different, this is also an ellipse. And finally, my yz plane, when I know that x is equal to k, well, I can plug this in and get k squared plus y squared over 9 plus z squared over 4 is equal to 1. Rearranging this, bringing that constant over to the other side, we get y squared over 9 plus z squared over 4 is equal to 1 minus k squared, which is just a constant. And again, we've got y squared and a z squared term that are both positive, and we've got different coefficients. And so again, this is an ellipse. And so let's try to sketch this. So with I'll just bring this original equation down here, x squared plus y squared over 9 plus z squared over 4 is equal to 1. All right, so if I'm looking, we've got our z, our y, and our x-axes here. These little letters say anything different, I can't see them. And we want to sketch this shape. Well, I'm going to see, I know that when z is equal to 0, I have an ellipse in the form x squared plus y squared over 9 is equal to 1. So I have an ellipse. What this tells me, so x squared plus y squared over 9 is equal to 1. I can find out where this intersects with the x-axis by plugging in a 0 for the y. I see that this interacts with the x-axis at 1. It's going to be very small. So here and here, this would connect to the y-axis at 3. When x is 0, y must be 3. And negative 3. So here and here. And so our horizontal trace would look like an ellipse, just like this. Okay, let's draw our other traces. Now we have this ellipse, x squared plus z squared over 4 is equal to 1 when k is 0. And here we're looking at the xz plane when y is 0. So on the xz plane, when our x value is 0, our z value must be 2, right about here, and negative 2. And when our z is 0, our x value must be 1 and negative 1. So we're going to have an ellipse that looks like this. Finally, on our yz plane, when our y value is equal to 0, our z value is going to be 2. And when our z value is 0, our y value is going to be 3. And if these points don't all match up and form some definite shape, then something has gone wrong. But this is good news. So let's just draw this ellipse on the yz plane. Okay. And now we can kind of see the shape. All right, and because all of these three traces are ellipses, we can call this an ellipsoid. And we do have the conclusion down here so you can get a better picture of what this actually might look like. But I just wanted to go through the process of graphing it so you could kind of follow along. All right. Example 5. Use traces to sketch the quadric surface with the equation z is equal to 4x squared plus y squared. So let's look at those traces. We've got our trace that is parallel to the xy plane, for which some z is equal to k. We plug z equals k into this equation, we get that k is equal to 4x squared plus y squared. And what kind of equation is this? Well, this is in the form of an ellipse. And now let's sketch as we go. So with this ellipse, we know that the major axis is the y. And if we just plug some of those values in, well, it's a little bit difficult because when k is equal to 0, this just comes to a point. But we have a trace that is an ellipse whose major axis is y. Let's make note of this. Which means that if this is our z, this is our y, and this is our x, that means this is going to be wider on the y-axis than it is on the x. So maybe this will look something like this. Okay? Now our vertical trace, we've got our xz, where y is equal to some k, and plugging that into our equation, we get that z is equal to 4x squared plus k squared. Well, this looks a whole lot like a parabola. Because we only have one term that is actually squared, because we know that this k is a constant, and this parabola is going to open upward. Or I should say, I'm sorry, I could say to the positive z-axis, but well, up is fine. So it's a parabola that opens upward on the xz plane. So it can look something like this. And then for our yz plane, the other vertical trace, we know that our x is going to be k. And if our x is k, then we get the equation c is equal to 4k squared. So we can just call that k squared plus y squared. And now this is also a parabola that opens up. And that makes sense. So we have that other trace going kind of from here to here. All right, so now we can see, while our drawing was not fantastic, here's a much better sketch for you, that because two of our traces are parabolas and one is an ellipse, this is an elliptic paraboloid, because we've got one ellipse and two parabolas. So this is an elliptic paraboloid. All right, example 6, use traces to sketch the quadric surface with equation z is equal to y squared minus x squared. All right, we've got our horizontal trace parallel to the xy plane where z is equal to k. Plugging in k, we get k is equal to y squared minus x squared. And what does this look like? Because we have a minus sign here, this is going to look like a hyperbola. And specifically, because this y squared is in front of the x squared, now we can rearrange this as negative k is equal to x squared minus y squared, right? Just multiplying everything by a -1. And in this form, I can more clearly see that this is a hyperbola that opens up and down, so whose conjugate axis is x. So it's going to look something like this when I've got my y and x axis. So let's kind of try to trace this. We've got our z, our y, and our x. And this is going to open up to the positive and negative y-axes. It's going to be this horizontal trace. And so something like this. Now for our vertical traces, we've got our xz plane, where y is equal to k, and plugging that in, we get z is equal to k squared minus x squared. Well, this looks like a parabola. And then where is it oriented? Well, it's oriented in the negative z direction. So it opens downward. And this again is on the xz plane. So we have a parabola that opens downward. So let's see, something like this. Okay, and finally, we've got our yz plane, where we've got the x equal to some k value. Plugging that in, we get z is equal to y squared minus k squared. And because this y squared is positive, this is going to be a parabola that opens upward. So on the yz plane, we have a parabola that opens upward. That's going to look something like this. And because we have these traces of a hyperbola, a parabola, and another parabola, this is going to be a hyperbolic paraboloid. If we were to complete this sketch, it would look something like this. Okay. I know I myself have trouble drawing these, but the good thing is that everything is on Webaside now, so you will just be selecting from a group of different pictures and choosing which one. So you won't actually have to do any sketches by hand, but the idea is that we can use these traces to find out what this might look like. And so this is what it actually looks like. Now these are just two different ways to draw this hyperbolic paraboloid. You can see that we're cutting into this thing just at different areas, specifically along the y-axis in this picture and in this picture. And we've got one more problem. Use traces to sketch the quadric surface with the equation x squared over 4 plus y squared minus z squared over 4 is equal to 1. So in the xy direction, that horizontal trace where z is equal to k, we've got x squared over 4 plus y squared, and I'm just going to move this over to the other side, is equal to 1 plus k squared. I have both positive signs. I've got a different coefficient attached to the x squared and y squared terms, and so I know that this is an ellipse. And more specifically, it is an ellipse whose major axis is the smaller of the coefficients, so I know that our major axis is x. All right, for our xz trace, we know our y is going to be some k. Plugging that in, we get x squared over 4. I'll just mentally bring this k squared to the other side, and I have minus z squared over 4 is equal to 1 minus k squared. So what do we have on the left-hand side? We have a minus sign here. And because we have one negative, we know that this must be a hyperbola. All right. Now, this k squared, this means that if k is greater than 1, then this is going to open up in a different direction than if the k is between 0 and 1, which would yield a negative on the right-hand side. So we'll just leave that as hyperbola for now. Finally, for the yz trace, our x is going to be some k, and so we are left with y squared minus z squared over 4 is equal to 1 minus, bringing this to the other side, 1 minus k squared. Again, we have one negative, and we are left with a hyperbola. Because we have an ellipse, a hyperbola, and a hyperbola, let's see what this might look like. Well, the horizontal axis is an ellipse. I'm sorry, the horizontal trace is an ellipse, I should say. We've got our z, we've got our y, and we've got our x-axes. And this ellipse has a major axis of x. And also I can see that as k gets larger, this ellipse is going to get larger. Our x and y values both need to be larger if our k is larger. And so I can see that because this is just longer in the x direction, because that's our major axis, I can draw an ellipse like this. And as our k gets more negative, our ellipse also gets larger. And now in the xz and the yz directions, so those vertical traces are both going to be hyperbola. And so it's going to look something like this. So not a great picture, but enough to see that this is a hyperboloid. Of one sheet. And we have a much better picture of this down here. Now, I will give you a warning here. You can use three-dimensional graphing software to figure out what this looks like. You can also use this cheat sheet here with the different equations and the different surfaces. However, I would encourage you to use traces because on the test you will not have all of these formulas, and I think it's a lot easier to make sense of these problems, to make sense of the traces and figure out what shape you have, than to try to just memorize all of these equations, because you are going to need to choose a sketch on your web assigned test. So we have a little bit of information here about graphing these in 3 dimensions, and then I'm not going to go through this in detail, but here are some applications of quadric surfaces that are actually pretty interesting, just for your reference. All right, that is it for this week. Thank you for watching these videos, and have a good day or night or whenever you are watching these.